Welcome back, students. In this video, let's look at disubstituted chair conformations. We already looked at cyclohexane and how to draw it in a chair conformation, and we also considered monosubstituted cyclohexane rings. But we can have more than one substituent on a cyclohexane ring. What we need to do now is look more at that down and up situation that we were talking about with axial and equatorial. When we consider a planar ring, so this ring that I've drawn here on the bottom left, this is drawn as if all the atoms in the ring are in the same plane. Now, you know for your chair conformation that they're not actually in the same plane, but this is just the best way that we can draw it without putting it in chair conformation. So this is planar, and then we need to look at how the substituents are drawn. There's wedged bonds and there's dashed bonds. Wedge bonds are trying to communicate up or out of the plane of the ring. Dashed bonds are trying to communicate down or behind the plane of the ring. So if I were to take this structure, I could draw this in chair conformation and make sure that the substituents that I've drawn, which are both methyls, right? If there's nothing at the end of either of them, they are methyls, that these substituents that I've drawn are indicating that they are above or below the plane of the ring. Let's do that together. I'm going to start by drawing some chairs. So here's one chair. And then I'm going to flip it and I'm going to draw my other chair. And when I go through this, I would need to choose a point to start. And this is part of the problem is if we don't choose the same place to start, it takes a lot of energy to make sure that we've come up with the same answer. So I'm going to tell you that I want you to start here and call this carbon number 1. And I want you to call this right here carbon number 1. And that way we can be sure that we're agreeing with one another. So if this carbon is carbon number 1, remember that dashed bonds are saying that they are down or behind the plane of the page. So at this position where I have called this carbon number 1, I'm going to take that 1 and I'm going to turn it into an axial position. This is axial pointing up. So here I have axial and it's up. If axial is up on that position, that means the equatorial position is going to be pointing slightly down on that same carbon. So that's axial up, this is equatorial down. If axial was up on that carbon, the next carbon, axial is going to be down. If axial was down on this carbon, then that means equatorial here is up. And so there's a pattern, right? There's two patterns. First pattern, looking at an individual carbon. One group must be up, the other group must be down. Second pattern, if we start where we called carbon number 1 and said axial was up on that carbon, then axial is down on the next carbon, which means axial's up on the next carbon, which means axial's down on the next carbon. So our goal was to have a methyl in that first position that was pointing down and away from the ring. So that means that I can come in, I can erase this. I want my methyl to be equatorial and down. Now, if that's carbon 1, then this is carbon 2 and this is carbon 3. So if this is carbon 1, this is carbon 2 and this is carbon 3. Those carbons that are bent like that, like carbon number 3 in the chair conformation, those are really hard to draw substituents on, but we're going to do it anyway. So the wedge bond is saying up and out of the plane of the page. So let's go back to our pattern. Carbon 1, axial was up. Carbon 2, axial was down. Carbon 3, axial is up. So on carbon 3, we have axial pointing up. And we had a wedge bond, and that's what we wanted. We wanted a bond that was up and away from the plane of the ring. So this one here is axial and up. Because remember, our dash we wanted down, and our wedge we want up. I'm going to go in and erase the work that is not actually part of my final answer. So I'm going to go in and I'm going to erase this, and I'm going to erase this, and I'm going to make this look more like a 1. Beautiful. So now I have an equatorial down and an axial up. When we do this chair flip, remember that we're taking this carbon I'm highlighting in yellow and we're pulling it down, right? So when we pull that down, I'm going to draw that arrow to show where it's coming down to. Where that arrowhead is pointing, that is carbon 1 on your next structure. I'm going to erase that arrow real quick because I feel like it muddies it up. So we had equatorial down on that first carbon. All our equatorials change to axials, but the fact that it's pointing down stays the same. So my equatorial pointing down is going to turn into an axial pointing down. This is carbon 1, so that makes this carbon 2 and this carbon 3. At our third position, we had an axial up. Now, when we've done the chair flip, we still have up, but our axial will change to equatorial. Again, I think it makes it easier for you if you start with drawing the axial so you can kind of get the angle for the equatorial looking good. And I think that looks good, so I can go in and erase my axial. And this is equatorial, and it's pointing slightly up. Now I want you to give it some practice. Here, I want you to translate these planar representations of rings into chair conformations. Once you've translated it into a chair conformation, go ahead and also flip the chair. In order for us to have the same answers, I want you to call this carbon 1 and this carbon 2. And I want you to call this carbon 1 and this carbon 2 and this carbon 3. And I'm going to give you your first, if that's your first chair, I want you to call this one carbon 1. That way, when we come back to compare, we can actually compare and make sure you have a correct answer. Otherwise, you're going to have way too much to look at and you will never feel confident that you have the correct answer. So give it a try. All right, let's walk through these two. The first thing that I wanted to point out is you might not be used to this notation right here, where this looks kind of unusual. This is a way to draw ethyl. We are showing that ethyl is wedged. We're showing that ethyl is dashed, and how we're doing that is with that dashed bond, but then this is one carbon and that's our second carbon, and that's how I know it's an ethyl. There's other ways to draw ethyl. You could just put the ET at the end for the abbreviation for ethyl if that was something that you preferred. Now let's draw the chair conformation. We've drawn the chair. Let's look at the fact that we have a wedge bond at number 1. So our wedge is going to be above the plane of the page, which at this position up is axial. So we're going to have a methyl there. Then at the second carbon, we have a dash bond. So if axial is up here, then axial is going to be down on the next carbon. So we can put in our ethyl pointing downward here because we have a trans situation, right? Trans is when you have two groups that are pointing opposite directions. One is up and one is down. And here you have an axial that's up, and here you have an axial that's down. Now we can go through the ring flip. I've drawn my other chair, and let's remember that this carbon that I'm highlighting in yellow is this carbon down here. Remember, we know that because we're pulling this carbon down, and where that arrow points to is where that carbon is on the second ring. Now, if our axial was up to start with, then when we get to that other side, we need an equatorial, but we need it to be up. So we're going to have equatorial up. Again, I think it's easiest to draw in the axial and then draw in the equatorial. So let's draw in the axial and then we can draw in the equatorial. So there's our equatorial up. This is carbon 1, just like how this was carbon 1. Now that we recognize that this is carbon 1 and our equatorial is up, let's go to carbon 2. At carbon 2, now we had an axial that was pointing down. And once we had an axial that was pointing down over here and we did the ring flip, now we're going to change that into an equatorial that's still pointing down. This is probably one of the hardest angles to draw, and I'm going to put in the axial that's pointing straight up here first. Depending upon the textbook that you use, depends upon if they draw the hydrogen in, I'm sorry, not the hydrogen, in this case the ethyl. If they're going to draw the equatorial position looking this way, or if they're going to draw the equatorial position looking this way. From my perspective, it is actually just about perspective. Like, are you looking at the ring from this side or are you looking at the ring from this side? But you might have a teacher who really has a strong opinion on which way it should be drawn. In the grand scheme of things, if you're in my class, as long as that is in a reasonable position, I am happy. So I can keep it right here, or I can take it and turn it back to the place that I first had it, which would be slightly this way. Use what works for you. I'm going to erase that axial position and then go ahead and say that this is equatorial and also still down. Notice how the ups and the downs aren't changing, right? That's key. The next one, we're going to do the same thing. I'm going to draw in those chairs. And we're going to call the same carbon, carbon number 1. I think it's really helpful to keep consistent when you're first starting. Technically, any carbon on the ring you could call carbon number 1. And now we have a wedge, and the wedge means it's coming up out of the plane of the ring. So we have a chlorine that is pointing straight up. Then this is carbon 2, this is carbon 3. At the third position, we have a methyl that is dashed, which means going behind the plane of the ring or down. Now at that third position, your axial is going to be up, so your equatorial is going to be pointing down. I'm going to erase the 3 so I can draw in the axial position. And this is the same idea as what we just saw in the previous one, right? You can either look from this way or you can look from this way and draw the angle for your equatorial. I didn't give myself a whole lot of space, so I guess I'm going to draw it this way. And then I'll just keep in that hydrogen here for reference. And that's a methyl, so you can either draw a CH3 and Me at the end of that or leave it blank and all would be fine. Then we go through and we end up flipping the ring. Remember that this becomes carbon number 1, this is 2, this is 3. So your chlorine was up to begin with and in the axial position. Now when we go through the ring flip, it's still going to be up, but it's going to be in the equatorial position. So now your chlorine will be here, equatorial, up. Here it was axial, up. Then at the third position, you had an equatorial that was pointing slightly down, and at this position, axial is pointing slightly down. So you have your methyl there. You might be thinking, like, how do you know when it's pointing up and when it's pointing down? First of all, loads of practice. Second of all, if you're ever uncertain, just know where one position is on each of your rings. Know that this is axial up, or know that here there's an axial down. If you know one position on the ring that makes you feel comfortable, then you can figure out the rest of them by using that pattern where it's, if axial's down here, on the next carbon axial's up, on the next carbon axial's down, and it keeps on just moving through that. And also the fact that on each individual carbon, you can only have an axial up, or an, on each individual carbon, you can have one up and one down. And in combination, those two things will help you figure out which positions are axial up and which positions are axial down, and same with the equatorials. like everything in organic chemistry, it's just going to take a lot of practice. We have one more idea to cover. In this idea, I want to look at, again, disubstituted rings and consider which ring is going to be more stable when there's two substituents present. So let's go ahead. If you want, you can pause me and we can draw the chair conformations as more practice, or I can just do them really quick. All right, so I drew these really quick. I want to look now at which conformation is going to be more stable. The one that's going to be more stable in this case should be kind of clear. Here, if we look at the structure or the conformation on the right-hand side, you have two substituents that are axial. That means you're going to have some serious 1,3 diaxial interactions. You have an ethyl that's going to be way too close to a methyl, all of which is going to be too close to the other hydrogen that is on this position here. So you're going to have an increased 1,3 diaxial interactions. Whereas in the structure on the left, which is what the equilibrium will lie to, right, we'll end up having a significant amount more of the conformation on the left because there's a minimization of 1,3 diaxial interactions because both substituents are in the axial position. That's wonderful. So we're going to say that if we label these, let's call this A and let's call this B. We'll say conformation A is more stable because both substituents are in equatorial positions, which minimize, I don't know if minimize is the right word, get rid of? Let's go ahead and erase which. And let's say, whereas B is much higher in energy because of the 1,3 diaxial interactions it experiences. Let's look at one more example. Here I changed this ever so slightly. I changed the ethyl from a dash to a wedge. We're going to draw another set of chairs for this, and then we're going to compare stability again. The ethyl is wedge, which means it's coming out of the plane of the page. Make that look a little prettier. And when it's coming out of the plane of the page, this is up. So now ethyl will be up here. Your methyl is dashed, and so here ethyl is up and axial, down is axial here, axial is up here, but you need an equatorial, and so you're going to draw an equatorial position so that it can be slightly down. We go through this process of chair flipping where now this carbon is this carbon, and we need that ethyl to still be pointing up, but axial is down on this position, so ethyl will be up on that position. So if that's carbon 1, here's carbon 2, here's carbon 3. You needed a methyl that was down, so methyl is axial here. Now, which one's more stable? And this gets a little bit trickier because in both situations, you have a substituent that is axial. So in both of these, you're going to have 1,3 diaxial interactions. So both conformations experience 1,3 diaxial interactions. The question becomes, which one experiences less? And hopefully you're starting to think about the fact that methyl and ethyl are not the same size, and that 1,3 diaxial interactions are looking at how groups can get too close to one another, Well, if the group is bigger, then isn't it easier to get close to something else? And so your ethyl being in the equatorial or in the axial position, that's going to be problematic. The ethyl being in the axial position ends up with greater 1,3 diaxial interactions because ethyl is a bigger group. So let's go ahead and say, we'll call this A again, we'll call this B. And we'll say A is higher in energy and thus less stable because the substituent in the axial position is larger in structure A than in structure B. So A has greater 1,3 diaxial interactions. So A experiences greater 1,3 diaxial interactions. And because A is less stable, then that means B is more stable because you have less 1,3 diaxial interactions due to the fact that the methyl is smaller than the ethyl. Let's wrap up. In this video, we looked at disubstituted cyclohexane rings. We drew chairs for them, we performed ring flips, and we also assessed the stability of the two different conformations and talked about why one was going to be more stable than the other. As always, thanks for your attention. This is Katoni signing out.